Welcome to part 2 of the lesson on logarithmic differentiation. So we saw in the first part that logarithmic differentiation is good for dealing with functions like this, or like, I forget what that example was, something like to the ln x. Basically anytime you have a variable in the base and the exponent, you need to use logarithmic differentiation, but it's also good for another type of function. So something like, I don't know, let's make this a quotient. Let's use that x squared minus 1 again, times, I don't know, square root of x plus 1, all divided by, what should we make it? Oh, I know. E to the x times, I don't know, x minus 1. So that's a pretty big function. So I want you to take the derivative of it. Which, I mean, I guess you know how to do that, right? It's a quotient, so you gotta use quotient rule. There's product in the quotient, so you gotta use product rule. You got some chain rule going on here. You know what? I'm going to make this a little harder. Power of 3. So, a couple chain, power of 2. Yeah. So, you could do that, right? Take a while. And actually, I'm going to challenge you to pause the video and find the derivative of that, using the techniques you know. So go ahead, pause it, and time yourself, because we want to compare the time it takes to do a regular to the time it takes using a new technique. So pause it. Okay, I give you enough time to pause it, and I guess you've done it, so it's probably like 10 minutes later. Now we're going to use a sort of shortcut for doing this type of question. So, same deal as before, we're going to do a technique where we take the ln of both sides. Now the question is, why are we doing that? I don't need to do it, right? We don't have a variable in the base and the exponent. We just have a really ugly quotient. Well, the reason we're doing it is because now we can apply some nice log laws to simplify this thing a lot. So we've got a quotient. Well, you need basically two log laws, or ln laws. I'll write them as ln laws. If you have ln of a times b, remember from advanced functions, that's equal to ln of a plus ln of b. And similarly, ln of a over b is equal to ln of a minus. What the heck happened there? It should be ln of b. Well, that looks better. So basically we're going to apply this rule. So this product here I can write as a sum, and the quotient I can write as a difference. And I'm going to do that all at the same time. Was it minus? Now this one's minus 2 because it's minus this whole thing. To the 2. And still not going to take the derivative. Because I can simplify further, right? Use another ln law. It's the one about exponents. That can come down. So that's going to make that derivative a whole lot easier. plus square root, so that exponent is half. That derivative's going to be a whole lot easier. Minus ln e to the x. Ooh, nice ln property there. What is ln e to the x? So hopefully you know that that's equal to x. And minus, again, the 2 can come down. Just going to move everything down there. And now I'm going to take the derivative of both sides. I'm not going to write that I'm doing it. I'm just going to do it. So, derivative of this, so we've got 3 all over, so this goes to the bottom, times, and we've got a bit of a chain rule, so that's the derivative of x squared minus 1, plus 2 on the bottom, so the 2 comes from the half, x plus 1, it's 1 over this, and chain rule, derivative is just 1, derivative of x is minus 1, plus the 2 over x squared plus 1 times 2x, and then that's all equal to again, we're going to have to get rid of that 1 over y. So just multiply by y times all this 6x over x squared minus 1 plus 1 over 2x plus 1 minus 1 minus 4x. Ooh, what happened? That's a minus 1, eh? Sorry about that. And, oh, okay, there's a little more simplifying, right? 6x minus 4x, so I'm out of room, so I'm just going to change this one to 2x and erase this one. So 6x minus 2x. They had the same denominator, so I could add them. And the y, you could put back what it was originally. So if you remember, y was originally this huge thing. I'm out of room, but yeah, just put back whatever y was there. And you can leave that, that's fine. Okay, so that's another time where you're going to use logarithmic differentiation. It's not necessary, as it was in the other case, but it helps a lot, right? You compared it to how long it took you to do it that first time, and I'm sure you all did that, and hopefully this was a lot quicker.